Welcome to Module 1. The primary source for each week's material is the week's module notes. The first 5 content areas in the Module 1 notes are review, normal distributions, random samples, a section that discusses pitfalls that can occur when using statistics, a section on hypothesis testing, and a section illustrating why statistical decision-making requires the analysis of variability in samples. There's a screencast for each of these 5 review content areas. The final section is new material. There are 2 screencasts. Screencasts talk through material that appears in the module notes. There's no requirement to view the screencasts. This screencast focuses on the normal distribution. I've moved to the next page in the note. Our example will involve a random variable y that represents the monthly production cost of a product expressed in dollars. The term random variable refers to the fact that random factors influence specific values, that is, specific monthly costs. Based on experience, we'll assume that the monthly production costs are distributed normally with a mean production cost of $44,000 and a standard deviation of production costs of $2,500. Here's a picture of that probability distribution. The mean of $44,000 is at the high point of the probability distribution. Half of all production costs are at or below $44,000 and half are at or above $44,000. Here are 2 well-known results involving normal distributions. The first says, for a normal distribution, 68% of all observations fall within 1 standard deviation of the mean. Typically, mu will represent the mean and sigma will represent the standard deviation. To say that 68% of observations fall within 1 standard deviation of the mean is to say that 68% are between mu minus sigma and mu plus sigma. For the monthly production cost example, since mu is $44,000 and sigma is $2,500, this says that in 68% of all months, 68 out of 100 months approximately, the production cost will be between $44,000 minus $2,500 or $41,500 and $44,000 plus $2,500 or $46,500. Part 2 of this result says 95% of all observations are within 2 standard deviations of the mean. For our production cost example, that is between $44,000 minus 2 times $2,500, $5,000, and $44,000 plus $5,000. So 95 out of every 100 months approximately will have production costs between $39,000 and $49,000. The third part of this result says 99.7% of all observations are within 3 standard deviations of the mean. For our production cost example, that's $44,000 minus 3 times $2,500, minus $7,500, and $44,000 plus $7,500. Or if you wish, 997 months approximately out of every 1,000 months will have production costs between $36,500 and $51,500. We note that this result can be viewed the other way around. Starting here at 3, 100% minus 99.7% is 0.3%, or 3 observations out of every 1,000 observations are outside of 3 standard deviations from the mean. So we would say in our production cost example, there'd be about 3 months in every 1,000 months where the production costs are either less than $36,500 or greater than $51,500. Up here at 2, looking at it the other way around, 100% minus 95%, 5% of months will have production costs that are outside, below $39,000 or above $49,000, and 100% minus 68%, 32% of months will have production costs that are either less than 41,500 or greater than 46,500. The second result is important when using a standard normal table to obtain probabilities for a general normal random variable, like our monthly production cost random variable y. The result says that when you begin with a normal random variable and subtract its mean and then divide by its standard deviation, you obtain a standard normal random variable with a mean of 0 and a standard deviation of 1. The letter Z typically is used to represent a standard normal random variable. Probabilities associated with Z's can be found by using a standard normal table, as we'll see in the U-try problem on the next page. Here's the U-try problem. U-try problems ask you to complete the solution and provide check solutions. The problem is, what is the probability that next month's production costs will be less than $50,000? Here's a standard normal table. You can use this table to look up Z probabilities. U-tries have text boxes that you can pull down to check your solutions. You should do the problem first and then pull down the text box to check your solution. I'll just pull down this text box and talk through the problem. The problem statement can be written: the probability of y being less than $50,000. We can change y to z units by subtracting from y the mean of $44,000 and then dividing by the standard deviation of $2,500. To keep the consistency of the inequality, however, we've got to do the same thing to both sides of the inequality. So we also have to subtract from $50,000 the $44,000 mean and divide by 2,500. This first random variable now becomes a Z, standard normal random variable, and then the second quantity is the number 50,000 minus 44,000 over 2,500, 2.40. Thus, to find the probability of y being less than 50,000, we can equivalently find the probability of a standard normal random variable being less than 2.0. To do this problem, we can use the standard normal table. We look for the number down to the tens digit, the 2.4, in the extreme left column. And then we find the hundredths digit of 2.40. We find the hundredths digit, the 0, up here in the top row. Where the 2.4 row intersects with the 0.00 column, we have the probability that we're looking for, 0.9918. In fact, this is pictured on the next page under the rest of the text box. Here we first entered to find the 2.4, looked up here to find the second digit, the 0.00. It's really that second 0 we're looking for, and at the intersection of the 2.4 row and the 0.00 column is the probability we're looking for. It looks like it's covered up a little bit there, 0.9918. We now know that the chance of next month's production cost being less than $50,000 is 0.9918, or if you like talking in percent, 98.18%. Said another way, the proportion of all months that will have production costs of less than $50,000 is greater than 99%. To use a standard normal table, we saw we need to convert the y random variable to a z random variable. If it's convenient to use Excel, we can avoid the need for us to convert to the z random variable to standard normal units. Excel will do that internally. If we want to use Excel to find the probability of y being less than 50,000, we simply have to type into a cell in Excel the following formula. Equals, always start off a formula expression with an equal, norm dis, normal distribution function, put in the y value, the value that we want to know the probability to the left of, 50,000. No commas in that 50,000 because in this function the commas will be used as separators. The next entry is the mean, 44,000. Again, no commas because the comma is going to be used as a separator. The standard deviation, 2,500. No commas in the standard deviation, just a comma. And finally, a true. The true simply says that what we're looking for here is the cumulative distribution, that is to the area to the left of 50,000 under this particular normal curve. If we didn't put a true in here, I'll show you what we get. If we put a false in there, for example, I'm going to need this picture, I think, which I actually didn't talk about. If we put a false in there, we'd be just getting the height of this little vertical line from the axis up to the normal curve, rather than what we're looking for, and that is this area, or if you wish, probability to the left of $50,000. So once we enter this formula into a Excel cell, we can tab out of it and we get the probability 0.991802 to more decimal place accuracy than we were able to pick up off of the table. Now, I've got here an Excel spreadsheet set up, and I practiced it, so let me get rid of it. And let me just pick a cell, and we're going to put in that formula, equals norm dis. Now, if you forget exactly how to type it, the Excel will remind you. It knows the direction in which you're going. Here are some formulas that you may be looking for. It says here to put in norm.dist, but in fact, if you didn't put the dot, you're going to get the same result, so I'm not going to bother with the dot. 50,000. No commas in the 50,000. The comma is a separator, 44,000. That's the mean, and then the 2,500, the standard deviation without commas. The comma is the separator, and then the true value and parents, and I'm ready simply to tab out of there and get the number we were looking for.